Imagine vast cities teeming with life, not cities of steel and concrete, but structures built by tiny living beings. These are the coral reefs. They are some of the most diverse ecosystems on Earth. Think of them as the rainforests of the sea. They cover less than 1% of the ocean floor, yet they support about 25% of all marine life. That is an incredible concentration of biodiversity. These vibrant underwater metropolises are truly a wonder of the natural world, showcasing the intricate dance of life and geology over vast timescales. Their existence speaks to the power of cooperation and the slow, patient artistry of nature. Coral reefs are not just pretty rocks, they are living structures. They are built by tiny animals called coral polyps. These polyps are related to jellyfish and sea anemones. Over thousands, even millions of years, these small creatures build enormous formations. Some reefs are so large they can be seen from space. The Great Barrier Reef off the coast of Australia is one such colossal example. It stretches for over 2,300 kilometers. That's like the distance from New York City to Dallas, Texas. These structures are a testament to the collective effort of countless generations of these minuscule builders, working tirelessly in the sunlit shallows of our oceans. These underwater cities are found in warm, shallow, clear waters. They prefer tropical and subtropical oceans. The temperature, water clarity, and sunlight are all crucial for their survival and growth. They are like delicate gardens, requiring specific conditions to flourish. If these conditions change too much, the reefs can suffer and even die. This makes them sensitive indicators of our planet's health. Their vibrant colors and complex shapes are not just for show, they're signs of a healthy, thriving ecosystem, a delicate balance maintained by the interplay of light, water, and life itself. So, what are these coral reefs? They are magnificent living ecosystems. They are built by tiny animals over immense periods. They are home to a stunning variety of marine creatures. They are vital for the health of our oceans and indeed our planet. Understanding how they form is like unlocking a secret to one of nature's most beautiful creations. It's a story of partnership, of chemistry, and of the relentless power of life to shape its environment. Let us embark on a journey to explore the birth and life of these extraordinary underwater realms, these cosmic jewels hidden beneath the waves. The master builders of these oceanic cities are called coral polyps. Each polyp is a tiny animal. Most are no bigger than a pencil eraser. Some are even smaller, like the head of a pin. Imagine a tiny, soft, sac-like body. It has a mouth at one end. This mouth is surrounded by a ring of tentacles. These tentacles are used to capture food. They sting and paralyze tiny floating organisms like zooplankton. The polyp then draws the food into its mouth to eat. It's a simple creature, yet it performs an extraordinary feat of engineering. These polyps are an ancient lineage. They have been building reefs for hundreds of millions of years. They are cousins to jellyfish and sea anemones. Like them, they belong to a group of animals called cnidarians. A key feature of cnidarians is their stinging cells called nematocysts. These cells are located on their tentacles. When a small prey animal brushes against a tentacle, these nematocysts fire tiny harpoons. These harpoons inject a toxin, subduing the prey. This efficient hunting mechanism allows these small, stationary animals to feed effectively in the bustling ocean currents. Coral polyps rarely live alone. Most are colonial organisms. This means they live together in large groups. These groups, or colonies, can consist of thousands, even millions of individual polyps. Each polyp is genetically identical to the others in its colony. They are essentially clones. They bud off from one another, slowly expanding the size of the colony. This colonial lifestyle is key to their reef-building capabilities. Together, these tiny individuals create structures far larger than themselves, a collective effort that shapes entire seascapes. Their interconnectedness is a marvel of biological organization. The role of these coral polyps in reef formation is fundamental. They are the living part of the coral. They are the architects and the construction workers combined. As they grow, they secrete a hard, protective skeleton beneath them. This skeleton is made of a substance called calcium carbonate. It is this skeleton that forms the very structure of the reef. Each new generation of polyps builds upon the skeletons of those that came before. Over vast stretches of time, these layers of skeletons accumulate, creating the massive, complex structures we call Coral reefs. It's a slow, patient process of creation. How do these tiny polyps build such massive structures? The secret lies in their ability to create a hard skeleton. This skeleton is made of calcium carbonate. Calcium carbonate is a common mineral. It is the same material that makes up chalk, limestone and marble. It is also found in the shells of many marine organisms like clams and snails. For coral polyps, it is the very foundation of their homes and collectively the reef itself. This mineral, drawn from the seawater, becomes the enduring legacy of these small creatures. Coral polyps extract calcium ions and carbonate ions from the seawater around them. These ions are dissolved in the ocean. The polyps have a special ability. They can combine these ions within their tissues. This process forms solid crystals of calcium carbonate. The polyp then secretes these crystals beneath its soft body. This creates a hard cup-like structure called a corallite. The polyp lives inside this protective cup. It's like building your own house around yourself, brick by tiny mineral brick. This intricate biochemical process is a cornerstone of reef formation. As the polyp grows, it continues to secrete more calcium carbonate. This makes its corallite larger and thicker. When a polyp reproduces, often by budding, the new polyp also starts to secrete its own skeleton. These individual skeletons fuse together. This creates the complex branching or mounding shapes of coral colonies. The specific shape depends on the species of coral. Some grow like trees, others like brains, and some form flat plates. Each form is an adaptation to its specific environment, optimizing for light capture or water flow. Over many generations, this process repeats. New polyps grow on top of the skeletons of dead ones. Layer upon layer of calcium carbonate accumulates. This slow, steady accumulation builds up the reef structure. It can take thousands of years for a large reef to form. The reef becomes a permanent feature of the seascape. It is a testament to the power of tiny organisms working together over geological timescales. The calcium carbonate they lay down becomes a record of past ocean conditions, a library written in stone, telling stories of Earth's changing climate and chemistry. Coral polyps are remarkable builders, but they don't work entirely alone. Many reef-building corals have a secret weapon. They have tiny single-celled algae living inside their tissues. These algae are called zooxanthellae, pronounced zooxanthellae. This is a crucial partnership, a form of symbiosis. Symbiosis means living together. In this case, it is a mutualistic relationship. This means both the coral polyp and the algae benefit. This internal alliance is one of the most important in the marine world, underpinning the productivity of entire reef ecosystems. The zooxanthellae are microscopic plants. Like all plants, they perform photosynthesis. Photosynthesis is the process where plants use sunlight to convert carbon dioxide and water into food, specifically sugars. The algae live safely within the polyp's cells, protected from grazers in the open ocean. In return for this safe haven, the zooxanthellae provide the coral polyp with a significant amount of food. These sugars, rich in energy, can supply up to 90% of the polyp's daily nutritional needs. This internal food source is vital for the coral's growth and survival, especially in nutrient-poor tropical waters. This partnership is also responsible for the beautiful colors of many corals. The zooxanthellae themselves have pigments. These pigments give the corals their vibrant yellows, browns, greens, and oranges. The coral polyp's tissue is actually transparent, so the color we see is primarily the color of the billions of tiny algae living inside. Without these algae, the coral tissue would appear clear, and we would see the white calcium carbonate skeleton underneath. This phenomenon is known as coral bleaching, a stark visual indicator of coral stress. The relationship between coral polyps and zooxanthellae is fundamental to reef formation. The extra energy supplied by the algae allows the corals to grow faster. It also helps them secrete their calcium carbonate skeletons more efficiently. Without this symbiotic boost, corals would build their skeletons much more slowly. Reefs as we know them, vast and complex, would likely not exist. This ancient partnership, forged over millions of years, is the engine that drives the growth of these spectacular underwater cities, a beautiful example of nature's interconnectedness and ingenuity. Section 5. The power of sunlight fueling the reef engine. Sunlight is the lifeblood of coral reefs. This might seem strange for an underwater ecosystem, but remember the zooxanthellae, the tiny algae living inside the coral polyps. These algae are plants, and like all plants, they need sunlight to perform photosynthesis. Photosynthesis is the process that converts light energy into chemical energy in the form of sugars. These sugars are then shared with the coral polyp, providing it with essential nourishment. Without sufficient sunlight, the zooxanthellae cannot produce enough food. This directly impacts the health and growth of the coral. This is why coral reefs are typically found in shallow waters. Sunlight can only penetrate so far into the ocean. The clearer the water, the deeper the sunlight can reach. Most reef-building corals thrive in depths of less than 50 meters, or about 165 feet. In this sunlit zone, known as the photic zone, the zooxanthellae receive ample light for photosynthesis. The intensity and duration of sunlight influence the rate of photosynthesis. Therefore, reefs are most abundant in tropical and subtropical regions where sunlight is strong and consistent throughout the year. The energy from sunlight captured by the zooxanthellae does more than just feed the polyps. It also significantly boosts the rate at which corals can build their calcium carbonate skeletons. The process of calcification or skeleton building requires a lot of energy. The sugars provided by the algae fuel this energy-intensive process. This means that in well-lit conditions, corals can grow faster and build more robust skeletons. This accelerated growth is crucial for the reef to keep pace with natural erosion and to create the massive structures we observe. Sunlight essentially powers the construction of the entire reef. If sunlight is blocked, perhaps by murky water or by being too deep, the zooxanthellae cannot photosynthesize effectively. This reduces the food supply to the coral polyps. The polyps become stressed and may even expel their algae. This leads to coral bleaching, where the coral loses its color and turns white. Prolonged lack of sunlight can starve the coral and ultimately kill it. So the availability of sunlight is a critical limiting factor for the distribution and health of coral reefs worldwide. It dictates where these underwater gardens can bloom and thrive. Section 6. Crystal clear sanctuaries, the ideal home for corals. Besides abundant sunlight, coral reefs have other specific environmental needs to flourish. One of the most important is clear water. Murky or turbid water filled with sediment and particles is detrimental to corals. Firstly, sediment can physically smother the coral polyps. If polyps get covered in a layer of silt or sand, they cannot feed properly. Their delicate tentacles can become clogged. Furthermore, they may not be able to extend their tentacles to capture food from the water column. This can lead to starvation and death for the tiny animals. Clear water is also essential for sunlight penetration. We've seen how crucial sunlight is for the zooxanthellae living within the corals. If the water is cloudy with suspended particles, less sunlight can reach the corals, especially those in slightly deeper areas. This reduces the rate of photosynthesis. Reduced photosynthesis means less food for the polyps and slower calcification rates. Therefore, areas with high levels of sediment runoff from rivers or coastal erosion are generally unsuitable for vibrant reef development. The clarity of the ocean is a window for the sun's life-giving energy. Water temperature is another critical factor. Reef-building corals thrive in warm waters. The ideal temperature range is typically between 23 and 29 degrees Celsius, or 73 to 84 degrees Fahrenheit. If the water gets too cold, coral growth slows down dramatically. If it gets too warm, even by just 1 or 2 degrees Celsius above their normal summer maximum, corals can become stressed. This heat stress can cause them to expel their symbiotic zooxanthellae. This is the primary cause of mass coral bleaching events, a serious threat in our warming world. Finally, corals require water with normal salinity levels. They are sensitive to changes in the salt content of the water. Areas near freshwater river mouths, where salinity can drop significantly after heavy rains, are not ideal for most coral species. They also need water that is relatively low in nutrients. While this might seem counterintuitive, high nutrient levels, often from pollution like agricultural runoff or sewage, can fuel the overgrowth of seaweed and other algae. These larger algae can then outcompete corals for space and light, smothering the reef. It's a delicate balance, a specific recipe for these underwater paradises. Section 7. Shadows over paradise, threats to coral reefs. Despite their ancient lineage and impressive structures, coral reefs are fragile ecosystems. They face a multitude of threats, many of which are caused by human activities. These threats are pushing many reefs around the world towards decline. One significant threat is pollution. Runoff from agriculture can carry pesticides, herbicides, and fertilizers into coastal waters. These chemicals can directly harm corals. Excess nutrients from fertilizers and sewage can also cause algal blooms. These blooms cloud the water, blocking sunlight, and can lead to an overgrowth of seaweed that smothers corals. Physical damage is another serious issue. Destructive fishing practices such as dynamite fishing or cyanide fishing shatter coral formations and kill marine life indiscriminately. Boat anchors dropped carelessly can break off decades, even centuries of coral growth in an instant. Coastal development, including port construction, dredging, and shoreline modification, can lead to increased sediment in the water. This sediment smothers corals and blocks sunlight, hindering their growth and survival. Even recreational activities, if not managed properly, like divers or snorkelers touching or standing on corals, can cause localized damage. Overfishing also poses a threat to reef health. Many fish species play important roles in maintaining the balance of the reef ecosystem. For example, herbivorous fish graze on algae, preventing them from overgrowing and competing with corals. When these fish populations are depleted through overfishing, algae can proliferate, harming the corals. The removal of keystone species can disrupt the intricate food web of the reef, leading to cascading negative effects throughout the community. It's a complex web of life, and pulling one thread can unravel others. Invasive species can also wreak havoc on coral reefs. These are species that are not native to a particular ecosystem and can outcompete or prey upon native organisms. For example, the lionfish, native to the Indo-Pacific, has become an invasive pest in the Atlantic and Caribbean. They are voracious predators with no natural enemies in their new environment. They consume large quantities of small reef fish, disrupting the ecological balance and potentially impacting the populations of fish that help keep reefs healthy. Managing these diverse threats requires a concerted global effort. Section 8. A warming world. The climate change challenge for reefs. Perhaps the most pervasive and severe threat to coral reefs globally is climate change. Our planet is warming due to the increasing concentration of greenhouse gases in the atmosphere, primarily from burning fossil fuels. This warming trend has profound consequences for the oceans. One of a major impact is rising sea temperatures. Corals are extremely sensitive to temperature changes. Even a small increase in water temperature, sustained for several weeks, can cause corals to expel their symbiotic zooxanthellae. This is coral bleaching. When corals bleach, they lose their primary food source and their vibrant color. They turn ghostly white as the transparent polyp tissue reveals the underlying calcium carbonate skeleton. If the warm water conditions persist, the bleached corals will eventually starve and die. We are witnessing mass bleaching events with increasing frequency and severity around the world. These events can affect vast areas of reef, turning once vibrant ecosystems into barren underwater graveyards. The Great Barrier Reef, for example, has suffered multiple severe bleaching events in recent years, a stark warning of the impacts of a warming climate. Another major consequence of increased carbon dioxide in the atmosphere is ocean acidification. The ocean absorbs about a quarter of the CO2 humans release. When CO2 dissolves in seawater, it forms carbonic acid. This increases the acidity of the ocean, or more accurately, lowers its pH. This change in ocean chemistry makes it more difficult for corals and other marine organisms like shellfish to build their calcium carbonate skeletons and shells. The building blocks they need, carbonate ions, become less available in more acidic water. Ocean acidification essentially slows down coral growth. It can also weaken existing coral skeletons, making them more vulnerable to erosion and storm damage. In some cases, if the water becomes too acidic, skeletons can even start to dissolve. This osteoporosis of the sea is a silent but deadly threat. It undermines the very foundation of the reef structure. Coupled with rising temperatures, ocean acidification presents a formidable 1-2 punch to coral reefs worldwide. Addressing climate change by reducing greenhouse gas emissions is critical for the long-term survival of these precious ecosystems. Section 9. Why reefs matter. a universe of importance. Coral reefs are not just beautiful underwater gardens, they are immensely important. Their significance extends to marine life, to human societies, and to the planet as a whole. For marine ecosystems, coral reefs are biodiversity hotspots. As mentioned, they support an estimated 25% of all known marine species, despite covering such a tiny fraction of the ocean floor. They provide food and shelter for thousands of species of fish, invertebrates, and other marine organisms. They are critical nursery grounds for many commercially important fish species, replenishing fish stocks in surrounding areas. For humans, coral reefs provide a wealth of benefits, often called ecosystem services. They are vital for coastal protection. The complex structures of reefs act as natural breakwaters. They absorb and dissipate the energy of waves and storm surges. This protects coastlines from erosion, flooding, and property damage. Millions of people live in coastal communities that are directly sheltered by coral reefs. The economic value of this protection service alone is estimated in the billions of dollars annually. Without healthy reefs, these communities would be far more vulnerable. Coral reefs are also a significant source of food and income for millions of people. Fisheries based around coral reefs provide protein and livelihoods for coastal populations, particularly in developing countries. Tourism is another major economic contributor. Snorkeling, diving, and recreational fishing on coral reefs attract millions of tourists each year. This generates billions of dollars in revenue and supports numerous jobs in the tourism industry. Furthermore, coral reefs are a source of novel medicinal compounds. Organisms found on reefs produce a variety of chemical compounds, some of which have shown promise in treating cancer, arthritis, and other human diseases. Beyond these tangible benefits, coral reefs hold immense cultural and aesthetic value. They are places of wonder, inspiration, and natural heritage. Their loss would diminish the biodiversity of our planet and impact human well-being in profound ways. Protecting coral reefs is not just an environmental issue, it is an economic issue, a social issue, and a moral imperative. The fate of these underwater cities is intrinsically linked to our own. As we explore the cosmos, let us not forget the wonders and responsibilities we have right here on our home planet in the vibrant, life-filled shallows of our oceans.